like within like a factor of 8 or something. Yeah. That means like the gap doesn't expand far before it's
Okay, welcome everyone. We have fewer people today, probably because of the snow, but also because of the retreat, the CFA retreat. There is a 2-day discussion about the future of the CFA, and that's why some people are not here. But nevertheless, we can see all the dedicated people, and we just had a fantastic talk by Jim Stone. And Jim, just like Uber drivers are being threatened by self-driving cars, I think the observers should be threatened by the advance of your simulations, because at some point you won't have to observe anything, we will just look at your results. So,
you say
no? Okay.
You say I'm a traffic
no.
accident waiting to happen? Is that what you're saying?
Okay, so we'll start today with Scott Kenyon, who is joining us by Zoom, and he will speak about dust as a solar shield. It's work he did with Ben Bromley that used to be at the ITC, and that is important for the future of the planet, potentially. And then we'll hear from Andy Burkert, who is visiting us from Munich. Where is Andy?
Yeah.
Oh, here. Good to see you. And he will talk about planet formation in turbulent molecular filaments, right? And then we'll hear from Jaya Adams about optimization techniques for exoplanet direct imaging. And finally, we'll hear from Jim again about a topic that he didn't have time to cover, and that will be dissipation and heating from turbulence in the weakly ionized interstellar medium. Take it away, Scott.
Well, thank you very much, Avi, and also thanks to Mark and Diana and Kareem for accommodating me in this way. I hope you can see my screen. You see the Earth, and so as Avi said, my title is Dust as a Solar Shield, work I did with Okay, so I should start? Okay, so I'd like to thank you all again for accommodating me in this way, and I hope the next time I give one of these talks, COVID will be less of a threat to me, and I'll be able to join you in person. So the work that I will describe today is work I did with Ben Bromley, a professor at Utah, my longtime colleague, an undergraduate at Utah, Samir Khan, and myself. So the idea is that we would like to understand how we could reverse the Earth's rising temperature. So there are sort of 3 general ways to do that. There's the mundane way. You can conserve energy, you can insulate your home better, you can do lots of things to try to conserve your use of fossil fuels. Current technology with renewables and carbon capture and things like that are an ever-increasing use, ever-increasing use of electricity or generation of electricity, and reduce our fossil fuel use. The third component is a more nerdy kind of thing, where geoengineering. There are groups that want to look at atmospheric manipulation, where you try to cool the planet by putting stuff in the atmosphere. And what I'd like to talk about today is space-based solutions, which is one of those we investigated. So the idea of a solar shield is a long-standing one. The idea is to put something between the Earth and the sun, reduce the amount of radiation we get from the sun, and thereby lower Earth's temperature, which is pretty straightforward. Roger Angel and many others have thought of having some kind of platform or set of platforms, and you need many. At the first Lagrangian point, these have the disadvantage that they are expensive to build and you need continuous fuel supply to maintain them. What we tried to think about was how would you place small particles at L1 and what kind of properties these particles would have to have and how would you get them there? So just to get everyone on the same page, here is a diagram of Earth's Lagrangian points. The sun is at the center, the Earth is off to the right, orbited by the moon. L2 is a point beyond the Earth relative to the sun, and that's where JWST is spending its time. We have the L3 point on the other side of the sun, L5 and L6, and in between the Earth and the sun, there's L1, and that's where the gravitational force from the Earth balances the gravitational force from the sun. So the idea is how do we get particles there and how long will they stay? So the properties of the particles that you need to have, obviously they have to have a large area to mass ratio because it's harder to put something at L1 the more massive it is, and if it has a small surface area, it doesn't cover much of the sun. So you have a large area to mass ratio, and so you want micron-sized or even submicron-sized particles. You want to limit the solar radiation pressure because for particles 1 or 2 microns and smaller, the solar radiation pressure will push them away from wherever you put them, and that's not very good. They'll go away on a very short time scale. So you'd like particles that forward scatter, because if they forward scatter instead of back scatter, a limited amount of the solar momentum from solar radiation goes into the particle and gets them moving. So these properties move you to consider fluffy, high porosity particles. And an example that we have today is snowflakes. Snowflakes are not a really good idea, set of particles to put at L1 because they would vaporize pretty quickly and they would go away. You also need a large mass. So if you want to occult, say, 2% of the sun's surface, you need 10 to the 10 kilograms in micron to submicron particles. And just to put that in perspective, JWST has a mass of 6,500 kilograms. So you need something like 15 million JWST mass equivalents at L1. So we did a lot of radiative transfer calculations and Mie scattering calculations to figure out, well, what kinds of particles actually would stay at L1 the longest. And a good example on Earth is coal dust. And just to give you a perspective on coal dust, the state of Wyoming manages to mine many times 10 to the 10 kilograms a year. So you could actually use a large fraction, if not all, of the coal dust from Wyoming if you wanted to launch it from Earth. Another option is lunar dust. There's a fair bit of lunar dust there that has accumulated on the moon over 4.5 gigayears of meteorite impact or meteor impacts and impacts of asteroids and comets and other things. So those are the two best examples. They have high porosity. They're very stable compared to other particles, and so you could put them at L1 for a long time. So how do you get the particles there? Well, if you want to launch 10 to the 10 kilograms from Earth, everyone knows how hearing out of JWST, a launch of something like 10,000 kilograms is really expensive. And if you want to multiply that by 10 to the 6, the amount of mass launched from the Earth is dwarfed by that, by many, many orders of magnitude. So if you launch from the moon, you take the advantage of the fact that the moon has a lower gravity. The moon is already moving, so that you get a little bit of boost from the motion of the moon. And it's closer to L1, especially if you launch near new moon. And so if you eject particles from the moon at around 2.5 to 3 kilometers per second, and 2.8 is roughly the escape velocity of the lunar orbit, then you can get particles just to L1. And maybe they'll stay there. So if you can get the particles there, and we identified the trajectories that would get the dust there, we did a number of n-body simulations with the moon, the Earth, the sun, Jupiter, Saturn, and Venus. Those are the main gravitational sources we have to worry about. And we worried about radiation. We included radiation pressure in these n-body simulations. So with the goal of reducing incident sunlight by 2%, we can get the particles to stay there for about a week. We get a temperature reduction from this about 1 degree Fahrenheit. So it's not a big reduction, and it's a lot of mass. So you have to think about if this is the way you really want to go. So we submitted this paper first to AAS journals, and you can find this paper if you just type PLOS Bromley into Google, you'll find it instantly. So we submitted it to AAS journals, and the editor said, this is geoengineering, and AAS journals don't do geoengineering. So, okay. So we racked our brains, and my wonderful wife, Margaret, came up with the idea of sending it to PLOS, which is the Public Library of Science. So PLOS, the regular PLOS journal doesn't really care about climate change, but there is an amazing new journal called PLOS Climate. And so we submitted the paper there. We got 3 reviews, which were positive, but wanted lots of changes because, after all, we're just poor astronomers or poor astrophysicists. And the climate people have a different language, and so they wanted changes of words here and there and various other things. The advantage of PLOS is that it's open access immediately. The day they post it, it is available to everyone in the world. The other advantage is that you have real-time statistics. And so you, as of earlier this morning, it had more than 10,000 views. And included in the 10,000 views is more than 1,000 downloads of the PDFs. It also has metrics that show you the news stories that have been written about a given paper. Again, as of this morning, we had about 260 news stories on 188 different outlets. They provide links to all the news stories. I didn't have room here, but they actually also provide links to Twitter. And that was really fascinating, reading all the Twitter comments. So with that, I will conclude. And if there's a time for a question or two, I'd be happy to take them. Thank you for your attention.
Thank you, Scott. One thing I heard from astronauts is that the dust on the moon is really sharp. In other words, if you were to hold it in your hands, it would cut them because it's fragments from impacts. And so my question is there a risk if some of this dust ends up settling on Earth? Did you consider that?
We did wonder where, since we did the n-body simulations, the idea is we sent a bunch of particles from the moon to L1. Right around new moon, you send this stuff off. It takes a day or two to get there. And then the solar radiation pressure disperses it. And it disperses it all over the solar system. And essentially none of it comes to Earth. And if like 10 to the minus 6% of it did come to Earth, it would burn up in the atmosphere because it's so small. So there's no danger to the Earth. There's no impact on the Earth. And the particles would be dispersed, and they would be a very, very small fraction of the mass of the small particles that are already in the inner solar system. So the inner solar system has around 10 to the 16 kilograms of stuff. So 10 to the 10 kilograms, we could make 1 million launches before we actually contributed an equal amount to the dust already in the inner solar system.
Other questions to Scott? Oh, go ahead.
So as a gardener, I have to ask, have you thought about the impact that something like this would have on anything that uses photosynthesis to survive?
I didn't quite hear that.
Photosynthesis?
Plants.
Any impact on plants if you block this light?
Sorry, if you could repeat that.
Impact on plants, vegetation, if you were to block...
Oh, okay, so that is, that's something we're not climate experts, so we don't really know. I mean, it's true that these kinds of mitigations are really sort of stopgaps. So you could lower the Earth's temperature by a degree or maybe 2 if you really, got something up to speed. And our point of view was that first, it's an astrophysics problem. We wondered, what can you do? How would you do it? How much mass would you need? And it's a daunting amount of mass. 10 to the 10 kilograms is not much mass, is not a trivial amount of mass. So if you reduce the Earth's temperature by a degree by this, plants presumably would suffer. But the way we think about this is that it's something you might want to do if nothing else has worked and you're trying to get reduce greenhouse gases, you're doing all the things you're supposed to do, and you need a little bit of extra time, say a few years. Of course, it's an amazing technological requirement. You have to build something on the moon and you have to launch things. So it's a lot better to, get renewable energy working and get rid of fossil fuels, and then you don't have to do this kind of thing.
The politicians an excuse to delay their action. That's another way to think.
Yeah, well, my feeling is that, everybody knows how much a launch costs. And launching something from the moon will cost much more than a launch from Earth because you have to get all the hardware to the moon and capabilities. And if you need, 10 to the 10 kilograms, that's a lot of launches. And, somebody wrote me and said that they estimated that this would cost something like 20% of the world's GDP for a decade just to be able to do it. So that's a lot. That's a lot of GDP. And you might just want to, fly less.
If there are no more questions, let's thank Scott again.
And thank you very much for having me.
Thank you for speaking about it. It's very, very exciting.
See whether this is on. Seems to be on. Okay, so I can start. So, thanks for inviting me again. I'm always happy to come when the snowstorms come. I love it in February, and there are rarely that many snowstorms in Munich left, so I have to come here to see them. Okay, so I would like to talk about something we have been working on recently, which is protoplanetary disk formation, and it is in the extended picture. It starts with a dense core, which is like a spheroidal Bonner-Ebert sphere, which is in gravitational instability, and then the core accretes material and begins to collapse. If the core has some rotation, people usually take some rigid rotation or so on, then the lowering momentum gas settles in the very center, forming a star, and around this a homogeneous gas disk forms, and the disk later on, by gravitational instability, breaks up into substructure, and maybe also by dust coagulation you get planets forming, and the disk then it basically evolves. And that is the standard picture which has been around for a very long time, and it's now being replaced by a more modern view which I would like to discuss. So what you see here is a turbulent filament in the interstellar medium called musca, and you can see that these filaments already contain cores. So the cores form in these turbulent environments, and if you look carefully then you see that the turbulence is subsonic. You see this in the lower part where the blue and the red lines show the random motion which you see along the line of sight, and the dashed part up there is the speed of sound, so you have subsonic turbulence. And the question is, first of all, how does this turbulence form, and secondly, how does it affect the core formation, and at the end the protoplanetary disk formation when the cores collapse. And that's something which we have been studying in a series of papers. So what we assume is very simple geometry. You see it up left, a cylindrical geometry where we have an accretion flow onto the cylinder, basically all the way forming a filament, and then we study what happens. And you see in the lower left diagram the velocity field and the density structure building up, and on the right you see the velocity dispersion along the line of sight. And what you can see is that we get a dense filament, of course, by setup. The filament becomes highly turbulent, irregular, driven by the inflow velocity and energy. And then you see on the right side that we get indeed subsonic turbulence. You know, the turbulence, the solid line shows the sound speed, and we get these kind of interesting fluctuations, and we get some equilibrium at the very end. Now, one of the problems here was we didn't include self-gravity, and so the filament became thicker and thicker and thicker, driven by the pressure, the turbulent pressure in the filament itself and the thermal pressure. And so the next step was to include gravity. And what you now see is something very different. The filament, of course, expands first, but then self-gravity actually limits it to a scale height or of order a tenth of a parsec. And when the filament reaches the critical line margin, m over L crit, which you see up there, which is 16.4 solar mass per parsec for reasonable sound speeds, then it forms a dense core which collapses. We were quite amazed when we saw this, because we thought that the filament has this turbulence, and so it shouldn't actually know about the turbulence. The line mass where it begins to collapse should be larger, but it isn't. The turbulence has no effect on stabilizing the filament, which is a very fascinating result in itself. So we'll always get 16.4 solar mass per parsec for collapse, which already is interesting if you want to understand the origin of the IMF, but I can't talk about this. Now, what we now did is we looked at this core. And what you can see is the core is not at all spherical, symmetric, and homogeneous. It is extremely turbulent, and this turbulence is something we didn't put in. It self-consistently arises from the turbulent filament when it condenses. And it's quite interesting, if you redo the simulation, you get a different result. You cannot predict what the core will look like and where in the filament it will form. It just happens automatically, naturally. So that's something which is much better than if you put in some turbulence by hand and you never really know what you get out is maybe what you have put in. So what the next step was to look at how this turbulent core evolves. And the first thing is we looked actually at the density profile. And what you see up there is the Bonner-Ebert sphere solution, which is a hydrostatic solution. The dashed line, the upper dashed line, is the ideal Bonner-Ebert sphere, including turbulent support, the turbulent velocity we see, and the solid line is our solution. So we thought, okay, this is a stable core, but when you look at the radial velocity, you see it's highly collapsing. It actually collapses with supersonic motion, and that was fascinating, because if an observer, you would say this is a stable core, but in reality it's not at all stable. It's collapsing, which is something you need to take into account as an observer. Bonner-Ebert sphere solutions don't mean it's stable at all. Now, what we then did, we zoomed into the core, and what you can see is when you go down on a scale from 0.4 parsec to 10⁻³ parsec, you see a disk forming. And this disk results from angular momentum you have somewhere in the turbulent core, but we didn't put it in. We didn't assume a shear flow or anything like that. The angular momentum is just in that part of the turbulence, which doesn't cancel all the angular momentum. And if you redo the simulation again, a new turbulent core forms, and the disk looks different. So every time you do redo the simulation, you get a different outcome, but the disks have the right scale. And what is even more interesting is that the disk has substructure. And we try to understand the substructure, and we found it's not self-gravity, it's not the planet formation that forms the substructure. The substructure comes from the turbulent core itself in the form of streamers that basically feed this kind of disk. And here you can see the disk edge on the right and face on the left, and you see these streamers which tell you there's an extremely inhomogeneous secretion that feeds the disk. And the disk knows about the turbulent core, and it knows about the turbulent filament in which the core forms. So there's a strong connection between the very large scales and what the final structure of the disk will be, and by that also what kind of planets at the end will form. So if you really want to understand the origin of planetary systems, you are forced to take into account the turbulent filament out of which the whole thing forms. So here you see the streamers even in greater details, and you see how important it is to take the substructure into account. Actually, it reminds me, this is a milliparsec scale if you want, or microparsec scale, but if you go to a megaparsec scale, you also have streamers, a cosmic web, that feed galaxies, and it looks very similar to this, just 12 orders of magnitude lower scale, so to say. And that tells us, basically what Jim Stone said, we need to do multi-scale astrophysics now. And indeed, there seem to be some observations which now actually, on the same scale, see these streamers feeding protoplanetary disk out of the environment. Now, we also included some magnetic fields, and if the magnetic field is weak on the left side, then the core doesn't really know about it. It evolves just driven by the turbulence. You get in this kind of core, and you get this disk. But of course, when the magnetic field strength is large enough, then the disks begin to orient themselves according to the magnetic fields. Magnetic field effects will become important, but still the substructure of the disk and how the disk then evolves into a planetary system is given by the turbulence, which is generated when the filaments are forming. So my conclusion all of this is the following. If you want to understand our origin, you need to understand life in the turbulent multi-scale universe. You need to understand how you get the turbulence and irregularities in the protoplanetary disks on a microparsec scale. But in order to understand that, you need to take into account the filamentary infall, the irregularity of the accretion onto the disk on the milliparsec scale. The filamentary infall comes from a turbulent core. The turbulent core, again, is a result of a turbulent filament. And so if you don't understand the turbulent filament on a parsec scale, you cannot understand the milliparsec scale core or the microparsec scale disk forming. Now, the filaments in interstellar medium are turbulent because there's a turbulent interstellar medium on the kiloparsec scale. And so you need to understand this kiloparsec scale to understand the parsec scale, microparsec, and milliparsec scales. And again, if you want to do this, you need to understand the cosmic web, because all these galaxies, which are star forming, are fed by gas from the cosmic web on the megaparsec scale, which again drives the dynamics of this kind of galaxies. So we have this problem that we have to take the multi-scale universe into account. And what we need to do is, you start with a gas particle on the larger scale, then you solve the equation of continuity and you follow the gas down all these scales till it ends up in this protoplanetary disk. And if we ever can do this, then we will finally be able to understand our origin. And with this, I would like to stop just in time.
The fact that you stopped at megaparsec, I understand that you don't believe in the multiverse. Questions? Ramesh and then...
So I was just curious, when you put the magnetic field, did you actually see MRI operating?
Yeah, well, okay, I think we couldn't really resolve it that well.
The resolution was not...
Yeah, the resolution is not good enough. But of course, that's a very, very good question to understand.
Smaller scale, that guy is going to be important.
Exactly, it must certainly be important. And of course, the disk, when the magnetic field string, as long as it begins to align, actually perpendicular to the filament, and then MRI effects will be important, and that's something to study in greater details. Yes, you're right.
Does the disk actually care about the filament, or if it's more like isotropic turbulence, do the same?
Does
the disk care about the filament, the structure of turbulence?
no, if without magnetic field, the disk structure depends on the core turbulence, which again depends on how big the turbulence is on larger scales. In fact, it is indeed true. If you start with a different setup, get a little more turbulence by driving more inflow, then you can get binaries forming. You get very complex disk structures. Let me see, here's one example, which shows if you take a more turbulent, generate a more turbulent filament, then you get actually binaries forming, and the disk changes completely, the whole system changes completely. So the protoplanet disks indeed know about the turbulence in the filaments. You know, you can get a correlation between both of this. So in that sense, it's indeed connected physics.
Yes, please go ahead.
Hey, what's the phase of these turbulent filaments on this scale?
You mean the phase? What do you mean by phase?
Neutral, ionized.
Oh yeah, no, these filaments are molecular. They're cold 10K molecular filaments, which we see. Yeah.
Yes, last question.
Is this a two-way street or just one way? So if it's just one way, could you simulate the large scale and get a sample and then simulate the smaller scale to a sample?
Yeah, well, the problem is, unfortunately, the larger scale is again connected to the smaller scales by feedback.
Yeah.
So at the end, you need a self-regulated cycle. Of course, well, this is what Jim is doing too. You know, we can zoom in, and then by the time we resolve the smaller scales, we cannot do any dynamics on the larger scales anymore, and that's what we right now have to deal with, and I'm not really sure we can really solve that problem. This is one of the questions, can we ever be faster than the universe? In the sense, if the universe takes 1 million years to do something, maybe we cannot do it faster. If we really want to take everything into account, then we have a problem. Yeah, okay.
On this sober note, let's do it.
Hey, hi everyone. My name is Jaya Adams. I'm a second-year grad student here at the CFA. And today I'll be talking to you about something that's really near and dear to my heart, imaging exoplanets. And this whole talk will really summarize essentially my 4 years as an undergrad and then up to about the past 4 months here at the CFA. So I'll start at the beginning. I was a first-year intern, and I started working on the giant accreting protoplanet survey. And my job, along with about 8 other interns, was to figure out whether or not these disks had planets forming within them. It was run by Professor Kate Follett at Amherst College, and this is me and some of the other 2018 summer interns at the time. And just to give some quick overview on the starting survey, so we wanted to take images of 14 disks at H alpha to see if there were any accreting protoplanets embedded within them. It was taken with Magellan adaptive optics at the VIS-AO camera over the course of about 5 years, so from 2013 to 2018. We had pretty good angular resolution because we were in the visible. We wanted disks with heavily depleted cavities that we could look into. And we're looking at very young systems because, again, we're trying to find planets that are still accreting material, so less than 10 million years, and systems up to about 400 parsecs. This is what we started with. And this image is also very near and dear to me because it's not the prettiest thing in the world, but myself, the other interns, and subsequent years of interns made these in DS9 to get an idea of what all the disks in our survey looked like and looking at those cavities. And I think it really shows you the diversity of the systems that we have. So we start with the survey, and what are we doing? We are trying to image the planets. And generally what that means is separating the starlight from the planet light somehow. In this case, we're also trying to separate the planet from any disk material in there. Generally, the way that this kind of imaging is done, once you have already taken the data, you've used any cool coronagraphs to help you block the starlight, is you're going to then use software. So we use algorithms to model the starlight in our images and subtract it to reveal any planets that are hidden. A quick image of that is just, this is some real data from the survey. Then we make a model of just the starlight, anything hidden in there, and we subtract it, and we're left with a planet, hopefully. So the overall formula for this is pretty simple. Data subtract model gives you planet. It turns out that this is really hard because modeling is really hard, and we did not find a single planet in our survey. We could have ended it there and said, well, there's just nothing in this data at all, except that we knew that there were at least 4 planets in there because they had been previously detected. So PDS70b and C, for example, like calcium-15b and C, were detections made in this exact data set, and yet somehow we could no longer recover those planets at all. It was a big problem. And it all came down to principal component analysis, and I'm going to explain this in the way that I was first taught it because this is what sticks in my brain. But I like to imagine that we're trying to make a model of an average human face. And principal component analysis at its core is a pattern finding technique. So our first principal components will be the things that are common to all of us. If I took an image of everyone's face in this room, we all have eyes, a nose, a mouth. So those are common patterns. Then you get a little more detailed. You might add some eyebrows and eyelashes to it. And then you add some ears. And finally, you have a model of a face as you add more detail. And let's say we wanted to use this model to find moles. I have a mole on my face, so this is me. And now I'm going to subtract the model that I made using all of our faces. And the hope is that at the end of this, we'll have just the mole. As you can imagine, it is not this straightforward. Just looking at all our faces, you probably can't capture all the detail on my face just by looking at your faces, or you might capture too much detail and be completely erasing my mole because you're picking up other features on other people's faces. And this is exactly what was happening with our planets in the disks and our principal component analysis. The algorithms we use have over 30 different parameters we can tune, and I'm just showing you 2 here. So on the y-axis, I have a simple annuli parameter. We can split our image into multiple annular zones and run PCA on them separately. And on the x-axis, I have what we call a movement parameter. How much sub-pixel motion am I allowing between images? And I ran principal component analysis on every combination of just these 2 parameters and colored the pixels by the signal-to-noise ratio of the detection in the N. And what I'm showing here is a pretty good one, A2M1, that combination. I don't know the exact SNR of this detection, but it looks really good, and I could probably convince someone that this was a planet. But then we move into some really bad parameter space, and we've completely lost the planet that was there. And then, of course, we have these average zones where you're detecting something, but it's not super clear. Maybe it's not at an SNR of 3 or 5 yet. This is the problem we are running into because me making this plot took weeks. And then if I got it wrong, it took some more weeks for me to remake it. And everyone is not going to sit down and do that for entire data sets. So we usually just end up choosing random parameter combinations, 2 or 3 of them, trying them, and then we say, oh, we never detected a planet in this data, and that clearly was not serving us very well. So we've identified the problem with imaging, and my thesis as an undergrad was focused on, can we use fake planets to help us find these real planets? Can this clue us into how PCA is working? So I started with what I'll call my continuum image sequence. We have our images of these disks, these systems taken at H-alpha, but we also took them at a nearby wavelength where we expect any planets that are in the data to be a lot dimmer or not there at all. And then I injected fake planets at a pretty good SNR at different positions and angles in the data. And what I really did here was I just took the stellar PSF and scaled it all the way down, put them in. Then I ran the grid search that I just showed you, and I won't get into detail there, but I ran it on a bunch of different parameters, and I found the best parameters for the fake planets and applied them to our H-alpha data to see if we could find any real planets. To summarize this all, can fake planets be a good proxy for how PCA works on real planets? And the answer in the end turned out to be, it does work. It worked really well. I tested this on one system specifically, HD 142527, which has an M-dwarf companion B, and I wanted this M-type star because it would be really bright and allowed me to check just how much these parameters made an impact. I was able to increase the SNR of the initially published detection by 5 sigma. And so the entire technique and how we chose these fake planets and what we did is summarized in my paper from last year. So then once we realized this work, we then applied it to the other 14 data sets, and we recovered all of our lost planets, which was a huge relief to us. So the fake planets are a good proxy. But beyond that, we actually detected a new planet, CS-CHA-b. And of course, this is still a potential candidate. It needs to be confirmed. And Kate is still working on this paper, but there is a submitted version on arXiv. This is really telling for us. It means that there's probably a lot of archival image data that we all have that may have missing planets embedded in them because we don't fully understand the nature of the algorithms we're using to find them. So this is just a rough start. We can't continue to do coarse grid searches forever. We're hoping to refine this a lot more as we move forward and get better at imaging planets as a whole. So yeah, thank you so much.
Perfect in terms of timing. Questions? Ramesh.
So Jaya, this is very nice. Just as a ballpark, how many PCA components do you use?
That's a great question. So that depends a lot on your image library, how many images you have. So I like to use about 20 to 50 principal components if I have an image library of about 100. But there are some images that have data sequences of thousands to 5,000 images within them. And I haven't fully tested how many principal components you need there, but you probably need to strike a balance of not getting too detailed, so you don't want to use all 5,000 images. But how little detail is too little, I'm not sure how it scales up. Yeah.
That would be a great thing to explore.
Yeah, definitely.
Right. Actually, a follow-up. You said something about multiple annuli.
Mm-hmm.
So what do? Do you fit independent PCAs for each annulus?
Yes, we do. And some people really like this technique because if they know a planet is in one specific region, one annular zone, they don't like to confuse PCA by considering the rest of the image. So they just look at that one annulus at a time. The problem is, though, that we don't understand exactly what effect this have because we haven't imaged that many planets in general. So yeah, it's still something to think about.
Any other questions? Please go ahead.
Jim, do you by chance find any previously unresolved stellar binaries through this method too?
That's a really good question. Unfortunately, no, we did not. Any binaries in the data we already knew about. So, yeah.
Okay, if there are no more questions. Oh, there is a question?
Yeah, I was just, you were going after planets like around stars with disks here. I was just curious in terms of like looking for planets around stars with disks versus without disks. Is there any reason you want to do one or the other?
Yeah, that's a really good question. So without disks, in principle, should be a lot easier because you don't have as much material to consider. And it turns out that one thing PCA is not able to capture yet that the human eye is what is a planet versus what is just a random blob in an image. It turns out our eye is really good at seeing something and saying that's a planet for sure versus not. But when we just hand it over to the algorithm, it's not that good. And so we've often had detections that our algorithm thinks looks like a planet, but we look at it and we say this is actually probably disk material. And the question of how to get around that, how to properly model the disk, I think is still an open one. Someone has to write the code to do that, to forward model a disk into these principal components. Yeah.
Let's thank Jaya again.
So great to be back again on a nice snowy day as well. First time I've seen snow this year, so it's great. So this morning I talked a lot about research directions we're going with studying accretion onto black holes and using a new version of a MHD code running on exascale architectures. And I wanted to mention one other project that a member at the Institute is leading on that problem, using that method, Levar Zamsky, on turbulence in the interstellar medium. But in order to describe the motivation for his project, I thought I would say something about a previous paper that another student at Princeton had worked on, Eric Mosley. Was in collaboration with Bruce Drain and myself and Kengo Tomita, again, modeling the cold neutral medium. And there was a sort of a limitation of this work that we're trying to extend now in this new work, so I wanted to set that up. And again, perfect timing to talk after Andy because he gave us a big picture of turbulence across the scales, not only in the interstellar medium, but in galaxies and in filaments. And so we're sitting right in the middle at the parsec scale. We're interested in turbulence in the interstellar medium at the parsec scale, in the multi-phase medium, and the particular phase we're most interested in is this cold neutral medium, where much of the material is not ionized, so it's really a fluid of neutral particles as well as some ions that are collisionally coupled to each other, with the magnetic field affecting the ions, but the neutrals just drifting across the magnetic field, except for these collisions. And so there's been a long history of studying MHD turbulence in the interstellar medium, usually using ideal MHD to start and moving on, and it continues with ever more sophistication. We're kind of using the same numerical models in this work as what has been done in that previous work. So in particular, this idealized, simplified model is just a periodic box of a size roughly a parsec, in fact, 20 parsecs in the case of Eric's work. There's a mean magnetic field initially in the box, and you add a turbulent driving force, a random force that stirs turbulence in the box, and you make the amplitude of that stirring large enough to give you the observed velocity dispersion, which on 20 kiloparsec scale is a few kilometers per second. So you generate supersonic turbulence on the largest scales, and then you can study the dynamics and the statistics of the resulting turbulent flow in that box. And so that's precisely what Eric did, with the additional aspect that he was following the thermodynamics of the gas. So first of all, because this is a weakly ionized gas, he was including ambipolar diffusion, which is the effect of the neutral drag on the dynamics. And he was doing that in the so-called strong coupling limit, where you evolve a single fluid, but you add a diffusion term in the induction equation to model the ambipolar diffusion. And then he was post-processing the resulting calculations to compute the temperature both from the thermodynamics of the turbulence, but also from cosmic rays and photoelectric heating, and also the cooling and line emission. And so then he was able to then create synthetic chemical models and therefore emission maps in various lines. So we could calculate what the abundance of, say, CH and neutral hydrogen would be along various sight lines in this turbulent box, and actually create synthetic maps. And I'm out of time already. And then try to compare that directly to the data. And by varying the parameters of the simulations, for example, you could vary the magnetic field strength, he could try to find the calculation that would best fit the data, and hopefully therefore sort of measure the properties of the cold neutral medium by using the observations to constrain what the actual results look like. So let me show you how that worked. So here was, should look similar to what Andy was showing you. Here's the column density in one of these turbulent boxes. The top row is for a weak magnetic field, roughly half a microgauss. A stronger field around about 4.5 microgauss on the bottom. And so this is just taking the raw data and just projecting it along the line of sight. But actually, because he's doing all this post-processing and chemical modeling, he can actually calculate, for example, the H2 line emission along the line of sight. And it looks quite different because the H2 is formed in certain locations in the flow, and in addition, only parts of it are excited. You only get H2 line emission, for example, in shocked regions. And so the actual observed intensity of H2 was not just following the observed column density, but quite different. In fact, you can actually pick out the shocks, which are exciting this H2 line emission, much more clearly in the synthetic image than you can in the actual column density map. So you could take these maps and compare them to observations of various regions in this medium and see how well you're doing. One quite telling statistic was to create histograms of, for example, CH plus and NH, and compare them again to observed sight lines in the interstellar medium. So for example, these plots show you the number density, the column density of CH plus versus neutral hydrogen. The colors are just basically PDFs, and you just basically take every grid cell in the calculation and you plot them as a two-dimensional phase dot in this two-dimensional phase space. And then the dots are the actual measured abundances from these different sight lines, data coming from this Wiselac paper in 2008. And you could compare these and see which ones fit the best. And it seems like the stronger magnetic field case, these two here, reproduce the data reasonably well, that you get the right, to rough agreement. The PDFs of the simulations, the simulated column densities are actually pretty good compared to the actual observed sight lines, where the weaker magnetic field's not as good, which is sort of expected because 4 microgauss is about what we, typical magnetic field you might expect in these regions. So this looked encouraging. But there's other information you can use, for example, from a completely different data set, namely the Planck satellite, which was not meant to measure the properties of the interstellar medium, but unfortunately for the cosmologists, they have to worry about this. They have this annoying foreground called the galaxy, and from that they can extract information about the magnetic field in the interstellar medium and the dust in the interstellar medium. In particular, you can measure this correlation and dispersion in the polarization angle versus the so I got to say it twice. It's the polarization versus the polarization angle. Namely, you could measure what the polarization is versus the scatter in the polarization. And so, that was the dotted line. There's a very nice correlation between these two quantities as measured from the Planck data. And again, you could calculate the same thing from these synthetic maps and try to compare the difference. Maybe not quite so discriminating, but it does seem again that the stronger magnetic field was following in the sort of bulk of the PDF better this correlation than the rest of the data. The weaker magnetic field has more scatter in the angle. It's a weaker magnetic field, gets pushed around more, and so the scatter was slightly different than this. So this was all sort of encouraging and very interesting, but there was this maybe skeleton in the closet, not the right word, but there was an approximation, a limitation in the calculation. Namely, he was using a single fluid model to model this weakly ionized gas using the so-called strong coupling limit for ambipolar diffusion, which requires making a very strong assumption about the ionization fraction in the gas and exactly the form of this term. And in fact, this approximation breaks down in very low density gas. When the alphane speed is very high in low density gas, this so-called strong coupling limit really doesn't work very well at all, and the ions are moving rapidly compared to the neutrals. There just isn't much collisional drag between the two of them. And you can't allow that. It generates unphysical heating, and so you have to assume an artificial limit to the ion-neutral drift velocity in the post-processing stage of the calculation. And in his case, he was assuming about 5 kilometers per second. And you can see that the results depended on that. If you look at the column density of CH+, for example, there's a big change in what the resulting values you would get depending on what you chose for this cutoff. Now, this 5 kilometers per second is reasonable. We think 1 kilometer would be too low. That's really not physical, but 5 kilometers is about reasonable. But should it be 5 or 10 or 4? You're not really sure. And there's a range of values that are sort of allowed, and these column densities are changing significantly over this range. And so that's a problem. But the only way around that is you really have to do the problem ab initio. You have to actually calculate the dynamics of the neutrals and the dynamics of the ions as two separate fluids. The ions follow the magnetic field and field Lorentz forces, the neutrals do not, and they're coupled by this collisional drag term, which is proportional to the velocity difference between the ions and the neutrals. And that's expensive to do because you've got to do twice the calculation. And moreover, it's even worse than that because the ions are relatively low density. Alphane speed in the ions is very, very high. And so sort of getting to your question earlier, the time skip gets very, very small, so it gets very expensive. So recently, Lev Arzamsky has been using this new version of Athena++, running on new hardware to redo these calculations, but in full two-fluid calculations. We're incorporating the neutrals and the ions as two separate fluids. And we're just driving turbulence and seeing what happens. The top row is the ions, the bottom is the neutral. You can see that immediately they behave differently. Now I am out of time. They can see dramatic differences in the dynamics of the two. In particular, the ions density is highly fluctuating compared to the neutrals. And I'll jump straight to the end to show, I think probably the most important result is that if you look at PDFs of the density, here's the ion density, the neutral density. A typical ratio between these two is 10 to the minus 2 in this cold neutral medium, roughly 1 ion for every 100 neutral particles. So each of these obeys PDFs centered around their mean. But what's important is the ratio is also a log normal PDF with a scatter of more than an order of magnitude, meaning that there's regions where the ion neutral fraction is varying by more than a factor of 10. And that dramatically changes not only the thermodynamics and heating, but also the chemistry. And so typically the models are run with assuming the ionization fraction of the ISM is a fixed number, but when you have turbulence, it's not a fixed number. There's going to be huge fluctuations in the ion velocity, in the ion density, for reasons I can explain if you like later, and that's probably important. So now we're redoing this post-processing analysis with this new data set to see how much this is going to affect the chemistry and sightlines, and we'll see what happens with that. I'll finish there.
Do you expect a charge exchange? In other words, the ability of one species to move to the other species to change things?
Yes, and so ionization recombination processes can play a role. For the bulk of the relevant dimensionless number is the ionization recombination time compared to, say, an eddy turnover time on that scale. In the densities we're talking about, those ionization recombination times are really very, very long compared. So generally, the ionization fraction is sort of frozen, but there could be regions if you have a higher ionization rate from nearby stars or something that could be different. It's quite straightforward to incorporate the ionization recombination processes as well.
Yep.
The distribution of ions versus neutrons, what determines the width of this?
It depends a lot on the magnetic field strength. That partially determines the width because the ions are coming into balance with the magnetic pressure fluctuations. Because they're low density, their pressure is low, and so they have to be compressed a lot to come into balance, and that's why you get such large fluctuations in the ion density. The stronger the magnetic field, the larger the B squared fluctuations and the larger the fluctuations in the ion density.
Lisa?
5 questions. I'll pick one for now.
All right.
But so you showed at the beginning this image that I was just whispering to Mike about of an H2
Right.
synthetic image.
Yes.
And neither you nor I knows of any infrared observations in H2 that would look like that.
Okay.
In line emission, that'd be great.
Right.
But my question is, did you also make synthetic images of shocks and things in this case with the real amiability?
No, we're in the middle of, being able to do something like that. That requires doing the H2 chemistry and then excitation processes to be able to put that.
But to Avi's point, we would love a telescope that could make that image.
Right.
Any other? Go ahead.
So in these two fluid simulations, both like neutrals and ions, so they live on the same mesh, or?
Yes.
Is it possible, I mean, from the movie it looked like ions have like much less structure, like on small scales, so is it possible to model low resolution, or?
You mean, I thought that, to my eye, it's like the.
Okay, yeah. No mind. Yeah. It's
So as far as the neutrals have lower, to my eye, structure.
Yes.
If we were really smart, we could probably figure out ways that we could, use different meshes. Post facto, that might be possible, but I think you always have to have this fine mesh for the ions, and once you have that, well, you might that's going to be all the expense anyways. You might as well just drag along the neutrals on the same mesh. But there could be cost savings like that you might be able to do. The real trick is the ion-neutral drag term can be very, very stiff, meaning that it's difficult to integrate numerically, and so you need a special implicit integrator to be able to handle the stiffness in the coupling term. But fortunately, there are straightforward ways to do that have been developed. There's lots of other interesting applications of this tool, for example, to protoplanetary accretion disks, which are also in this weakly ionized regime and are currently mostly modeled using the strong coupling limit, which is probably a bad approximation for the wind region at the surface of the disk. And so we're also planning to do some ion-neutral models of the MRI in protoplanetary disks to see how that might change the turbulence in the upper layers.
So Jim, it looks like there is a lot of interest in your work. You should come and visit us more often. Thank you for
Thank you.
2 talks today.
Right.